Okay, constant velocity unit. This is what we studied this unit. First thing we did was to play around with toy cars. We looked at battery powered cars, and this is what we saw. For battery powered cars, they had a constant velocity. They could either have a negative velocity, like this one, constant negative velocity. It's starting in front of the origin and moves in the negative direction. Or we could have a constant positive velocity, where it's starting at 0 or right before 0, and moves in the positive direction, like this car. We're going to attach this piece of paper to it, and it will put a bunch of dots on it. Notice the dots are equally spaced. That tells us it's moving at constant velocity. We also played around with pullback cars, and for pullback cars we didn't see constant velocity. What we saw was they had either sped up or at the very end of their motion they slowed down. This one's going to be speeding up in the positive direction. Notice it gets faster and faster and faster. So that's how we started off. Basically, we saw that there are three different types of motion with the cars. We saw type 1, where it didn't move, it just stopped, it stayed at rest. Type 2, where it was moving at constant velocity, either going in the positive direction or in the negative direction, but what that means is constant speed and constant direction. Or type 3 is when it speeds up or slows down. In this unit, the only thing you need to know is type 1, where it's moving at constant velocity, or it's just not moving. So the goal of this unit was to describe motion. There are 4 ways you must be able to describe motion. First, written in words. Second, with graphs. Third, with motion maps. And fourth, with equations. There are 2 types of graphs you need to be familiar with: position time graphs and velocity time graphs. For type 1 motion, that's where it's not moving. The position time graph might look like this. This is where it's standing in front of the origin and not moving. Notice we have X with an arrow above it, that stands for position, and T, those labels have to be on the graph. We might have no motion at the origin, so here it's not moving and it's sitting at the origin. Or maybe we have no motion and it's behind the origin. Those are all type 1 motion. For each one of those, the velocity time graph looks the same. So no matter where it's standing at, if it's not moving, the velocity time graph looks like this: 0 speed. For type 2 motion, again, this was constant velocity. We could be having it starting behind the origin, moving in the positive direction at a constant velocity. We could have it starting at the origin, moves with constant positive velocity. Or we can have it starting in front of the origin, moving at constant positive velocity. For each one of these, the velocity time graph looks the same. I have to go back. And in that case, what it looks like is that the velocity time graph is a constant, but now it's positive instead of 0. Or we could have negative velocity. So in this case, we have it starting in front of the origin. It moves at a constant negative velocity. This one is starting at the origin with a constant negative velocity, and this one's starting behind the origin with a constant negative velocity. For all of these, the velocity time graph looks the same. So no matter where it starts at, the velocity time graph, if it's moving at a constant negative velocity, looks like this. Now these you do not need to know for this unit, but if you're wondering, okay, what does the speeding up or slowing down look like? So all of these are going to be speeding up in the positive direction from rest, starting at different locations. On the far left, it's starting at the origin. In the middle, it's starting in front of the origin. And in the far right, it's starting behind the origin. They all start at rest, not moving, and then they speed up in the positive direction. For all of these, they're going to be slowing down to a stop in the positive direction, starting at different locations. So on the far left, it's starting behind the origin, and it's slowing down in the positive direction to a stop. In the middle, starting at the origin, and it's slowing down to a stop in the positive direction. In the far right, it's starting in front of the origin, and it slows down as it moves in the positive direction to a stop. Again, none of these do you need to know. Okay, so now let's look at motion maps. For type 1 motion, when it's not moving, if it's starting in front of the origin, this would be kind of like what the motion map would look like. Or let's say it's starting at the origin. This is what the motion map would look like. For constant velocity motion, this is what the motion map would look like. Let's say it's starting in front of the origin. In this case, it's starting at 2 and has a constant positive velocity of 3 meters per second. So that's what it would look like. Let's say it's starting in front of the origin, in this case 10 meters, and now it has a constant negative velocity, in this case negative 2 meters per second. This is what the motion map would look like. You need to be able to go from one type of description to another. In this case, we're given a position time graph. Let's see if we can put it into words. In words, it would be starting at 3 meters, the object moves in a positive direction at a constant velocity of 2 meters per second for 3 seconds, then it stops for 2 seconds, then it moves in a negative direction at a constant velocity of negative 3 meters per second for 3 seconds. The velocity time graph looks like this. The displacement during the first 3 seconds is the area of the green rectangle, in this case 6 meters. The displacement during the last 3 seconds is the area of the red rectangle, which is negative 9 meters. The displacement from 1 to 7 seconds would be the areas of the green rectangle and the rectangle, so that would be a positive 4 meters plus a negative 6 meters, gives you negative 2 meters. For these two types of graphs, the position time graph and the velocity time graph, you also need to be able to write or draw the motion map. And this is what the motion map would look like. It starts at 3 meters. It moves to the right in the positive direction at a constant 2 meters per second for 3 seconds. Then it stops for 2 seconds. And then it moves to the left in the negative direction at a constant negative 3 meters per second for 3 seconds, ending at 0. Here's another velocity or motion map, another position time graph. Let's translate this one into words as well. Starting at 7 meters, the object moves in the negative direction at a constant negative 1 meter per second for 3 seconds. Then it moves in the positive direction at a constant velocity of 1 meter per second for 3 seconds. Then it moves in the negative direction at a constant velocity of negative 2 meters per second for 2 seconds. This is what the velocity time graph would look like. Let's find the displacement by looking at the area for the velocity time graph. The displacement during the first 3 seconds is the area of the red rectangle, which is negative 3 meters. The displacement during the next 3 seconds is the area of the green rectangle, which is positive 3 meters. And the displacement during the last 2 seconds would be the area of the red rectangle again. In this case, it would be negative 4 meters. Let's say we need to figure out what is the displacement from 2 to 7 seconds. That would be the area of the red rectangle, the green rectangle, and the other red rectangle. So negative 1 meter plus 3 meters plus a negative 2 meters, given a total of positive 1 meter. So for the position time graph and the velocity time graph, we need to be able to draw the motion map, and this is what it would look like. Let's use these 3 different tools to figure out what is the displacement from 2 to 6 seconds. Displacement, which is delta x, is equal to the final position, xf, minus the initial position, xi. So the final position is 7 meters. That's at 6 seconds. The initial position is 5 meters. That's at 2 seconds. So 7 minus 5 is 2 meters. We can get that from the position time graph, and we can get that from the motion map. Let's look at how we get that from the velocity time graph. That would be finding the areas. So from 2 to 6 seconds, that's going to be the area of the red rectangle and the green rectangle. So negative 1 meter plus 3 meters. And that gives us the same answer, 2 meters, for the displacement. You need to be able to describe how motion is different for two different objects. So here's a position time graph for object 1 and object 2. How are their motions different? Well, object 2 starts behind object 1. It moves in the opposite direction, and it's faster. Well, how do we know that? The way we know is by looking at the y-intercept, the slope, and the steepness. So since it's, for object 2, since its y-intercept is lower, that would mean it starts behind. Since its slope is not negative, it's positive, that means it's going in the opposite direction. And since it's steeper than object 1, that means it's faster. Let's do a couple calculation problems. A race car travels 448 miles around a circular track. It takes 2.7 hours to cross the finish line, which is also the starting line. The average speed of the car is blank miles per hour, round to the nearest tenth. The way you find average speed is by taking the total distance divided by the total time. In this case, the total distance is given as 448 miles, and the total time is given as 2.7 hours. Dividing these on a calculator and rounding to the nearest tenth gives us 165.9 miles per hour. Let's try one that's slightly different. Notice the one before this was average speed. This one's different. This is average velocity. Susie travels 26 meters in the positive direction in 15 seconds. Then she walks 9 meters in the negative direction, so she turns around, in 7 seconds. Her average velocity in meters per second is blank. Answer to the nearest tenth. Okay, so for this one, average velocity is given as displacement. Remember that speed is total distance. This is not. This is displacement. But they're both over total time. So in this case, to figure out what displacement is, I'd have to see how they're moving. At first they move in the positive direction 26 meters. But then they backtrack. They backtrack 9 meters. So I need to subtract 9 meters. The total time would be 15 seconds for the first part and 7 seconds for the second part. So I have to add those together. When I add 26 plus a negative 9, I get positive 17. When I add 15 and 7, I get positive 22. Using a calculator and dividing 17 by 22, I get 0.8 meters per second. That's all the material you need to know for tomorrow's test. Good luck.